A neutron star begins its existence in one of the most violent events in the universe. It is born from the death of a massive star, a star many times larger than the Sun, which has reached the end of its life and can no longer sustain the delicate balance between gravity and nuclear fusion. For millions or even billions of years, such a star has been engaged in a constant struggle between the inward pull of gravity and the outward pressure created by nuclear reactions in its core. Hydrogen has been fused into helium, helium into heavier elements, and so on, building layers like an onion, each layer representing a different stage of nuclear burning. Eventually, however, the star reaches a point where it can no longer produce enough energy to support itself. When the core of the star becomes dominated by iron, the process of energy production effectively stops. Iron is the most stable element in terms of nuclear binding energy, which means that fusing iron does not release energy, but instead consumes it. At this stage, the star is in a critical and unstable state. Without outward pressure from fusion to counteract gravity, the core begins to collapse inward under its own immense weight. This collapse happens in a fraction of a second on cosmic timescales, but during that moment, the fate of the star is completely rewritten. As the core collapses, protons and electrons are forced together under extreme pressure. Under normal conditions, these particles are separate, but in the collapsing core of a massive star, the density becomes so extreme that electrons are pushed into protons, forming neutrons. This process is known as electron capture. In an incredibly short time, the core of the star transforms from a structure made of atoms into a dense mass composed almost entirely of neutrons. The result is an object so dense that atomic structure itself is no longer able to exist in its usual form. The collapse of the core is not a gentle process. It happens with extraordinary speed and releases a tremendous amount of energy. As the core collapses inward, the outer layers of the star are also affected. When the core suddenly becomes incompressible at nuclear densities, it rebounds slightly, creating a shock wave that travels outward. This shock wave, combined with a flood of neutrinos released during the collapse, helps to tear the star apart in a massive explosion known as a supernova. The outer layers of the star are expelled into space at tremendous speeds, enriching the surrounding interstellar medium with heavy elements forged during the star's life. What remains after this explosion is the neutron star. It is the collapsed core of the original star compressed into an object with a diameter of only about 20 kilometers, yet containing more mass than the Sunday. This means that an entire star has been squeezed into a sphere smaller than a city. The density of this object is almost impossible to comprehend using everyday comparisons. A single teaspoon of neutron star material would weigh billions of tons on Earth. The formation of a neutron star represents one of the most extreme transformations in nature. Matter that once existed as ordinary atoms is crushed into a state where protons and electrons no longer exist separately. Instead, the object is composed almost entirely of neutrons packed together so tightly that there is almost no empty space between them. This state of matter cannot exist under normal conditions on Earth and only forms under the extraordinary pressures found in collapsing stellar cores. Immediately after its formation, a neutron star is incredibly hot. Temperatures can reach billions of degrees, and the object radiates enormous amounts of energy, particularly in the form of neutrinos. Over time it cools, but it remains one of the densest and most exotic objects in the universe. Despite its small size, it contains immense gravitational power due to its concentrated mass. The surface of a neutron star is unlike any surface found on planets or ordinary stars. It is not solid in the traditional sense, but rather a thin, ultra-dense crust made of nuclei packed tightly together. Beneath this crust lies a region where matter behaves in ways that are not fully understood. As pressure increases with depth, atomic nuclei are squeezed so tightly that they may form exotic structures, sometimes described as nuclear pasta, due to their shapes resembling sheets, tubes, or other complex formations. Gravity on the surface of a neutron star is extraordinarily strong. If a person could somehow stand on its surface without being destroyed instantly, they would experience a gravitational force billions of times stronger than on Earth. Even light is affected by this gravity, which is why neutron stars can bend the path of light traveling near them. This extreme gravity also means that any matter falling onto the surface is accelerated to immense speeds, releasing huge amounts of energy upon impact. Neutron stars are not static objects. Many of them rotate extremely rapidly, often spinning multiple times per second. This rapid rotation is a result of conservation of angular momentum. When the original star collapses, its rotation speed increases dramatically, just as a spinning ice skater rotates faster when pulling their arms inward. Some neutron stars rotate hundreds of times per second, making them some of the fastest rotating objects in the universe. Despite their small size, neutron stars can have powerful magnetic fields. These magnetic fields are generated by the motion of charged particles within the star and can be trillions of times stronger than Earth's magnetic field. These intense magnetic fields can accelerate particles and produce beams of radiation that extend far into space. The combination of rapid rotation and strong magnetic fields gives rise to one of the most fascinating phenomena in astrophysics, the pulsar. A pulsar is a type of neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the neutron star rotates, these beams sweep across space like the beam of a lighthouse. If Earth happens to lie in the path of these beams, we observe regular pulses of radiation at extremely precise intervals. Pulsars are incredibly stable rotators. Their rotation periods can be measured with extraordinary precision, sometimes rivaling the accuracy of atomic clocks. This stability makes them valuable tools for studying a wide range of astrophysical phenomena, including testing the effects of general relativity and detecting subtle changes in space-time. The discovery of neutron stars and pulsars fundamentally changed our understanding of the universe. Before their discovery, such extreme states of matter were purely theoretical. The realization that nature could create objects of such density and energy challenged existing models of physics and opened new fields of research in high-energy astrophysics and nuclear physics. The formation of neutron stars also plays a crucial role in the cosmic cycle of matter. When massive stars explode as supernovae, they release heavy elements into space. These elements are later incorporated into new stars, planets, and even living organisms. In this way, neutron stars are part of a larger process that recycles matter throughout the galaxy. In addition to their role in element formation, neutron stars also serve as laboratories for studying matter under extreme conditions. The densities and pressures found inside them cannot be replicated on Earth, making them unique, natural experiments in physics. By studying neutron stars, scientists can test theories about the behavior of matter at nuclear densities and explore the limits of known physics. The birth of a neutron star is not an isolated event, but part of a larger cosmic story. It represents the final stage in the life cycle of a massive star, a cycle that begins with the formation of stars from clouds of gas and ends with the redistribution of matter across the universe. Each neutron star is therefore both an endpoint and a beginning, marking the transition from one form of cosmic structure to another. As we begin to explore neutron stars in greater detail, we enter a realm where the laws of physics are pushed to their limits. These objects challenge our understanding of matter, energy, and gravity, and they reveal just how diverse and extreme the universe can be. The birth of a neutron star is not just the death of a star, but the creation of one of the most extraordinary objects in existence. After a massive star collapses in a supernova explosion, what remains is not just a single uniform object, but a layered remnant shaped by extreme forces that push matter beyond ordinary physical limits. The outer layers of the star are blown away into space, enriching the galaxy with heavy elements, but deep inside, at the very center of the collapse, a radically different form of matter is created. This remnant is the neutron star, a compact core where gravity has crushed atoms into a state that defies everyday understanding. To understand what is left behind, it is important to follow the final moments of the star's life in more detail. As the core of the massive star collapses, the pressure rises so quickly that atoms are literally destroyed. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. This process happens almost instantaneously, and in that brief moment, the structure of matter changes fundamentally. The familiar world of atoms, molecules, and chemical bonds ceases to exist in the core. What remains is a dense fluid of neutrons packed together under extreme gravitational pressure. This transformation marks the boundary between ordinary matter and degenerate matter. In normal conditions, atoms are mostly empty space, with electrons orbiting a tiny nucleus. But in the core of a collapsing star, that empty space disappears. The electrons are squeezed into the nuclei, and protons are converted into neutrons. The result is matter that is incredibly dense and fundamentally different from anything found on Earth. This is neutron degenerate matter, and it is what supports the structure of a neutron star against further collapse. However, the collapse does not stop immediately at this stage. During the supernova explosion, the outer layers of the star are violently expelled into space. These layers contain elements that were forged during the star's lifetime, including carbon, oxygen, silicon, and iron. When these materials are ejected, they spread into the surrounding interstellar medium, where they will eventually become part of new stars and planets. In this way, the death of one star contributes to the birth of future cosmic structures. What is left behind is the compact core, but even this core is not uniform. A neutron star is structured in layers, each with distinct physical properties. The outermost layer is the crust, which is incredibly thin compared to the overall size of the star. Despite its thinness, this crust is extremely strong. It is composed of a lattice of atomic nuclei, packed together so tightly that they form a rigid structure. This crust behaves like a solid, but it is far denser and stronger than any material found on Earth. Beneath the crust lies a region known as the inner crust. Here, the pressure is so great that neutrons begin to leak out of atomic nuclei, forming a sea of free neutrons alongside the remaining nuclei. This region is highly unusual because it contains both nuclear structures and free particles interacting under extreme conditions. It is here that matter begins to take on exotic configurations that cannot exist at lower densities. As we move deeper into the neutron star, we reach the outer core. In this region, matter is no longer arranged into distinct atomic nuclei. Instead, it exists as a dense fluid of neutrons, protons, and electrons in equilibrium. The pressure is so high that particles are forced into extremely close proximity, and quantum mechanical effects dominate their behavior. The interactions between particles in this region are governed by the strong nuclear force, which operates only at very short distances, but becomes the dominant force under these conditions. Deeper still lies the inner core of the neutron star, which is one of the most mysterious regions in astrophysics. The exact nature of matter in this region is not fully understood because the densities involved exceed those that can be recreated in laboratory experiments. Some theories suggest that neutrons themselves may break down into their constituent quarks, forming a state of matter known as quark matter or strange matter. If this is the case, then the inner core of a neutron star may contain exotic particles and phases of matter that have never been directly observed. The transition from the crust to the core of a neutron star represents one of the most extreme changes in physical conditions anywhere in the universe. Density increases dramatically as one moves inward, reaching values that are difficult to comprehend. A neutron star is so dense that a single cubic centimeter of its material would have a mass comparable to a mountain on Earth. This extraordinary density is what allows such a small object to contain more mass than the Sunday. Despite their small size, neutron stars have incredibly strong gravitational fields. This gravity is so intense that it significantly affects the behavior of matter and radiation near the surface. If an object were to fall toward a neutron star, it would be accelerated to a significant fraction of the speed of light before impact. The energy released in such a collision would be enormous, producing intense bursts of radiation. The surface of a neutron star is often described as a solid crust, but this is a simplification. In reality, the surface is a dynamic boundary between the rigid outer crust and the fluid interior. It is composed of tightly packed nuclei arranged in a crystalline structure, but this structure is constantly under stress due to the star's rotation and magnetic fields. Small changes in the crust can lead to sudden releases of energy, known as starquakes. Starquakes are similar in concept to earthquakes on Earth, but they are driven by different forces. As the neutron star cools and its rotation slows over time, stresses build up in the crust. When these stresses exceed the strength of the material, the crust can suddenly shift, releasing energy in the form of radiation and sometimes altering the star's rotation speed slightly. These events provide valuable information about the internal structure of neutron stars. Another important feature of neutron stars is their extreme rotation. Many neutron stars rotate very rapidly, sometimes hundreds of times per second. This rapid rotation is a direct result of the collapse process. As the original star's core shrinks, its rotation speed increases dramatically due to conservation of angular momentum. This is similar to how a spinning figure skater rotates faster when pulling in their arms, but on a far more extreme scale. This rapid rotation has important consequences for the structure and behavior of neutron stars. It causes the star to become slightly flattened at the poles and bulged at the equator. It also contributes to the generation of strong magnetic fields. The combination of rotation and magnetic fields plays a crucial role in shaping the environment around the neutron star. Magnetic fields in neutron stars are among the strongest in the universe. These fields are generated by the movement of charged particles within the star's interior and are amplified by the star's rapid rotation. In some cases, the magnetic field can be trillions of times stronger than Earth's magnetic field. These intense fields can influence the motion of charged particles in space and produce powerful beams of radiation. The interaction between rotation and magnetic fields is what gives rise to pulsars, but even before reaching that stage, neutron stars already exhibit complex electromagnetic behavior. Charged particles are accelerated along magnetic field lines, creating radiation that can span across the electromagnetic spectrum, from radio waves to gamma rays. The environment around a neutron star is therefore extremely energetic. Space near the surface is filled with high-energy particles, intense magnetic fields, and strong gravitational effects. Any matter that comes too close is quickly torn apart and accelerated to extreme velocities. This makes neutron stars some of the most hostile environments in the universe. Despite this hostility, neutron stars are not static or unchanging objects. They evolve over time. As they age, they gradually lose energy through radiation and magnetic braking. Their rotation slows, and their magnetic fields can weaken or change structure. However, this evolution occurs over extremely long timescales, often millions or billions of years. The formation of a neutron star also leaves behind a surrounding supernova remnant. This is a vast cloud of gas and dust expanding outward from the original explosion. Over time, this material mixes with the interstellar medium and contributes to the formation of new stars and planetary systems. In this way, neutron stars are part of a larger cycle of cosmic recycling. The study of neutron star remnants provides important clues about the nature of supernova explosions. By analyzing the composition and structure of these remnants, scientists can reconstruct the conditions that existed during the collapse of the original star. This helps improve our understanding of stellar evolution and the processes that govern the life cycles of massive stars. Neutron stars also serve as natural laboratories for studying fundamental physics. The conditions inside them cannot be reproduced on Earth, making them unique environments for testing theories of matter, gravity, and nuclear interactions. Observations of neutron stars help constrain models of nuclear physics and provide insight into how matter behaves at extreme densities. Ultimately, what is left behind after a supernova is not just a remnant, but a new form of cosmic object that pushes the boundaries of known physics. A neutron star is both the end of a massive star's life and the beginning of a new phase of extreme matter in the universe. It represents a bridge between ordinary stellar matter and the most exotic states of matter known to science. Inside a neutron star, matter exists in a state that has no true equivalent anywhere on Earth. It is a realm where the familiar structure of atoms collapses completely, and the very concept of empty space inside matter disappears. To understand the interior of a neutron star is to step into conditions where gravity dominates every interaction, and where quantum physics and nuclear physics merge into a single extreme environment. This is not a solid object in the ordinary sense, nor is it a liquid or a gas. It is something far more exotic, a continuous gradient of ultra-dense matter held together by gravity so intense that it reshapes the behavior of particles themselves. The outermost region of a neutron star, the crust, already defies ordinary intuition. At first glance, it appears solid, and in many ways it behaves like a rigid material. But unlike rock or metal on Earth, this crust is composed of atomic nuclei, arranged in a crystalline lattice, packed so tightly that almost all empty space between atoms has been eliminated. Electrons are no longer bound to individual atoms in the usual way. Instead, they form a degenerate sea of particles moving freely through the structure. This electron sea helps stabilize the crust and gives it unusual electrical and thermal properties. As we move deeper into the crust, pressure increases dramatically. The weight of the material above compresses everything below it with relentless force. At a certain depth, atoms become so compressed that electrons are forced into nuclei, combining with protons to form neutrons. This process, known as neutronization, transforms the composition of matter itself. The nuclei become increasingly neutron-rich until they can no longer hold together in conventional forms. At this stage, matter begins to dissolve into a mixture of free neutrons and neutron-rich nuclei. This transition marks the beginning of the inner crust, one of the most unusual regions in astrophysics. Here, nuclei no longer exist as isolated structures. Instead, they are surrounded by a fluid of free neutrons that have escaped from atomic cores. These neutrons are not bound in place, but move through the space between nuclei, forming a kind of quantum fluid. This mixture of nuclei and free neutrons creates a complex environment where both nuclear forces and quantum mechanical effects dominate behavior. As pressure continues to increase with depth, the structure of matter becomes even more exotic. Nuclei begin to distort and merge into unusual shapes due to competing forces between nuclear attraction and Coulomb repulsion. Instead of forming simple spherical nuclei, matter organizes into complex configurations, often described as nuclear pasta. These structures are named based on their shapes, which resemble sheets, tubes, and other elongated forms. Examples include lasagna, like sheets of nuclear matter, spaghetti, like filaments, and even more complex geometries. These nuclear pasta phases are not just theoretical curiosities. They are believed to play an important role in the mechanical and thermal properties of neutron stars. The arrangement of matter in these structures affects how heat flows through the star and how the crust responds to stress. In some cases, these structures may influence how the star emits radiation and how it evolves over time. Beyond the inner crust lies the outer core of the neutron star. This region is fundamentally different from anything closer to the surface. Here, the distinction between individual nuclei disappears entirely. Matter exists as a dense fluid composed primarily of neutrons, with a smaller fraction of protons and electrons. The particles are so closely packed that quantum mechanical effects dominate their behavior. In this environment, particles are not localized in the way they are in ordinary matter. Instead, they behave as overlapping quantum states governed by the rules of degenerate matter. In the outer core, neutrons are the dominant component. These neutrons are packed so tightly that they are forced into extremely high energy states due to the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state. As a result, neutrons in the core of a neutron star resist further compression, creating a form of pressure known as neutron degeneracy pressure. This pressure is what helps support the neutron star against further gravitational collapse. However, neutron degeneracy pressure alone does not fully explain the stability of the star. Strong nuclear forces also play a critical role in balancing gravity at these densities. The interplay between quantum degeneracy pressure and nuclear interactions creates a complex equilibrium that determines the structure of the star's interior. As we move deeper still into the neutron star, we reach the inner core. This region is the most mysterious and least understood part of the entire structure. The densities here are so extreme that even neutrons may begin to break down into their constituent particles known as quarks. If this occurs, the matter inside the core may transition into a new state known as quark matter or strange matter. In quark matter, neutrons are no longer intact particles. Instead, their internal components, quarks, are freed and exist in a deconfined state. These quarks interact through the strong nuclear force, forming a dense, fluid-like medium. Some theories suggest that strange quarks, one of the heavier types of quarks, may also appear in this environment, leading to an even more exotic form of matter known as strange matter. If strange matter is stable, it could represent the true ground state of ultra-dense nuclear material. The existence of quark matter inside neutron stars is still an open question in physics. It cannot be directly observed with current technology, and scientists must rely on indirect evidence such as mass measurements, gravitational wave signals, and theoretical models. However, if confirmed, it would represent one of the most significant discoveries in modern physics, revealing a completely new phase of matter. The conditions inside a neutron star are not static. They evolve over time as the star cools and loses energy. Initially, a newly formed neutron star is extremely hot, with temperatures reaching billions of degrees. Over time, it cools by emitting neutrinos and thermal radiation. However, even as it cools, its internal structure remains locked in place by gravity and quantum forces. One of the most important aspects of neutron star interiors is the role of superfluidity. In certain regions, particularly within the inner crust and outer core, neutrons are believed to form a superfluid state. In this state, particles move without friction and can flow in a coordinated quantum manner. Superfluidity arises when particles pair up and condense into a single quantum state, allowing them to behave collectively rather than individually. This superfluid behavior has important consequences for the dynamics of neutron stars. It affects how the star rotates, how it responds to changes in angular momentum, and how energy is distributed within its interior. In some cases, sudden changes in rotation known as glitches are thought to be caused by interactions between the superfluid interior and the rigid crust. The interior of a neutron star is also influenced by superconductivity. In regions where protons exist alongside neutrons, these protons may form superconducting states, allowing them to conduct electricity without resistance. This superconductivity interacts with the star's magnetic field, helping to shape its structure and evolution. The combination of superfluidity and superconductivity makes the interior of a neutron star a highly complex and dynamic system. It is not a simple static structure, but a layered, interacting environment where quantum mechanics governs large-scale behavior. These properties are essential for understanding phenomena such as pulsar timing, irregularities, and magnetic field evolution. Gravity inside a neutron star is so strong that it significantly distorts space-time itself. According to general relativity, massive objects curve the fabric of space-time, and neutron stars represent some of the most extreme examples of this effect outside of black holes. Time passes more slowly near the surface of a neutron star compared to distant observers. This means that clocks placed near a neutron star would run noticeably slower than those far away. The internal structure of a neutron star is therefore shaped not only by nuclear and quantum forces, but also by relativistic effects. The balance between gravity, quantum pressure, and nuclear interactions determines the overall stability of the star. Small changes in any of these factors can lead to significant changes in behavior. Despite its extreme conditions, the interior of a neutron star is not chaotic. It is structured according to well-defined physical principles, even if those principles operate under conditions far beyond everyday experience. The layers of the star are arranged in a gradual transition from nuclear lattice structures at the surface to exotic quantum fluids at the core. Understanding the interior of neutron stars is one of the greatest challenges in modern astrophysics. It requires combining knowledge from nuclear physics, quantum mechanics, and general relativity. Each of these fields describes part of the picture, but none alone can fully explain the behavior of matter at these extremes. Neutron stars therefore serve as natural laboratories for testing the limits of physics. They allow scientists to explore conditions that cannot be recreated on Earth and to probe the behavior of matter under the most extreme pressures and densities known in the universe. Every observation of a neutron star provides new clues about the fundamental nature of matter itself. Inside these extraordinary objects, the universe reveals a hidden layer of reality where matter is compressed to its ultimate limits, and the familiar rules of physics are pushed to their breaking point. Gravity is the defining force of a neutron star, and it is responsible for shaping every aspect of its existence. On Earth, gravity is something we experience as a gentle pull that keeps us grounded, that gives weight to objects, and that governs the motion of planets and moons. But on a neutron star, gravity ceases to be gentle or familiar. It becomes an overwhelming force that dominates every interaction, bends space-time in extreme ways, and compresses matter into forms that cannot exist anywhere else in the universe. To understand gravity at the edge of physics, it is important to begin with scale. A neutron star typically contains more mass than the Sun, yet it is compressed into a sphere only about 20 kilometers across. This means that a single neutron star packs solar mass into a city-sized volume. The result is a gravitational field so intense that it dramatically alters the structure of space and time around it. If Earth had the same surface gravity as a neutron star, the entire planet would be crushed into a thin layer of matter only a few centimeters thick. At the surface of a neutron star, gravity is not just strong, it is overwhelming in a way that defies everyday intuition. If an object were dropped from even a small height above the surface, it would accelerate to a significant fraction of the speed of light before impact. There is no gentle descent, no slow accumulation of speed. The gravitational pull is so intense that motion becomes extreme almost immediately. This means that any matter approaching the surface is subjected to enormous tidal forces and energy release upon contact. Tidal forces are one of the most important consequences of strong gravity. These forces arise because gravity is not uniform across an object. The side of an object closer to the neutron star experiences a stronger gravitational pull than the far side. On Earth, tidal forces are responsible for ocean tides due to the Moon's gravity. But near a neutron star, tidal forces become unimaginably strong. An object approaching the star would be stretched vertically and compressed horizontally in a process often described as spaghettification. The difference in gravitational pull across even a small object can become so extreme that it is torn apart before reaching the surface. These tidal effects are especially important when considering matter falling onto a neutron star from a companion star in a binary system. As gas and material spiral inward, they are heated and stretched by tidal forces, forming an accretion disk. In this disk, matter moves at extremely high speeds and becomes heated to millions of degrees due to friction and gravitational compression. This process releases enormous amounts of energy, often in the form of X-rays, making accreting neutron stars some of the brightest X-ray sources in the universe. Gravity near a neutron star also has profound effects on light itself. According to general relativity, gravity bends the path of light by curving space-time. On Earth, this effect is extremely weak and difficult to measure. But near a neutron star, space-time curvature is so strong that light paths are significantly distorted. This means that light emitted from the surface of a neutron star does not travel in straight lines, but follows curved trajectories around the star. This gravitational lensing effect allows distant observers to see parts of the neutron star that would otherwise be hidden. In some cases, light emitted from the far side of the star can be bent around the surface and reach an observer, effectively allowing more than half of the star's surface to be visible at once. This extreme bending of light is one of the most direct observable consequences of strong gravity and provides important information about the star's mass and radius. Another important effect of gravity on neutron stars is gravitational time dilation. According to general relativity, time passes more slowly in stronger gravitational fields. This means that clocks closer to a massive object run slower than clocks farther away. On a neutron star, this effect becomes extremely significant. Time near the surface of a neutron star passes noticeably slower compared to distant regions of space. If an observer could hover near the surface, they would experience time differently compared to someone far away in space. This time dilation is not just a theoretical curiosity. It has practical implications for how we observe neutron stars. Signals emitted from the surface, such as radiation pulses or thermal emissions, are affected by this gravitational redshift. As light climbs out of the strong gravitational field, it loses energy, shifting toward longer wavelengths. This means that radiation emitted from a neutron star appears redshifted when observed from a distance. The gravitational redshift also provides a way to measure the strength of gravity on neutron stars. By analyzing the spectra of emitted light, scientists can determine how much energy has been lost as it escapes the gravitational field. This allows for indirect measurements of the star's mass and radius, which are crucial for understanding its internal structure. One of the most extreme consequences of neutron star gravity is the effect on space-time itself. In general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. Near a neutron star, this curvature becomes extremely pronounced. Space and time are both distorted in such a way that the geometry around the star is significantly different from flat space. This curvature affects not only light, but also the motion of particles and objects in orbit around the star. Orbits near a neutron star can behave in ways that are very different from those around less massive objects. Stable orbits exist only at certain distances, and closer to the star, orbits become unstable and can lead to rapid infall. In some cases, matter can orbit the star at speeds approaching a significant fraction of the speed of light. The combination of strong gravity and rapid rotation in neutron stars leads to additional relativistic effects. Many neutron stars rotate extremely quickly, and this rotation interacts with their gravitational field to produce frame dragging. Frame dragging is a phenomenon in which space-time itself is pulled along with the rotating mass. This means that space around a neutron star is not only curved, but also twisted by its rotation. Frame dragging affects the motion of particles and radiation near the star. It can influence the structure of accretion disks, the behavior of magnetic fields, and the emission of radiation. In extreme cases, it can even contribute to the launching of jets of particles along the magnetic poles of the star. These jets can extend far into space and carry enormous amounts of energy. The surface gravity of a neutron star is so strong that escape velocity becomes a significant fraction of the speed of light. Escape velocity is the speed required for an object to break free from a gravitational field. On Earth, this velocity is about 11 kilometers per second. On a neutron star, it can exceed half the speed of light. This means that any matter attempting to leave the surface must overcome an enormous gravitational barrier. Because of this extreme gravity, neutron stars are highly efficient at trapping matter and radiation. Once material falls onto the surface, it is extremely difficult for it to escape. This leads to the accumulation of energy and matter in specific regions, particularly near magnetic poles, where accretion can be channeled along magnetic field lines. The interaction between gravity and magnetic fields is particularly important in neutron stars. Strong magnetic fields guide the motion of charged particles and can channel accreting matter onto small regions of the surface. This creates hotspots that emit intense radiation. As the neutron star rotates, these hotspots can produce regular pulses of radiation, which are observed as pulsars. Gravity also plays a role in shaping the long-term evolution of neutron stars. Over time, neutron stars lose energy through radiation and particle emission. As they cool and slow down, their internal structure adjusts to maintain equilibrium. However, the strong gravitational binding ensures that they remain extremely compact and stable over long periods. In some cases, neutron stars exist in binary systems with other stars. In these systems, gravity plays a central role in the transfer of mass between the two objects. If the companion star expands or loses material, the neutron star can capture this matter through its gravitational field. This process can lead to periods of intense X-ray emission and dramatic changes in the system's behavior. If enough matter accumulates on a neutron star, it may eventually exceed a critical mass limit. Beyond this limit, known as the Tolman-Oppenheimer-Volkoff limit, the neutron star can no longer support itself against gravitational collapse. In such cases, it may collapse further into a black hole. This transition represents the ultimate consequence of extreme gravity, where even neutron degeneracy pressure is not enough to resist collapse. The study of gravity in neutron stars provides a unique opportunity to test general relativity in extreme conditions. These objects represent natural laboratories where space-time, curvature, quantum effects, and nuclear physics all interact simultaneously. Observations of neutron stars help scientists refine theories of gravity and improve our understanding of how space-time behaves under extreme conditions. In many ways, neutron stars represent the boundary between known physics and the unknown. They exist in a regime where gravity is so strong that it reshapes the behavior of matter, light, and time itself. Yet despite these extreme conditions, they remain stable objects that can persist for millions or billions of years. Gravity at the edge of physics is not just about force, but about the structure of reality itself. Neutron stars reveal that gravity is not merely something that pulls objects together, but a fundamental feature of the universe that shapes the very fabric of space and time. Pulsars represent one of the most precise and extraordinary natural phenomena in the universe. They are neutron stars that rotate at incredible speeds while emitting beams of electromagnetic radiation from their magnetic poles. As these beams sweep across space, they create a pattern of regular pulses that can be detected from Earth, much like the rhythmic flash of a lighthouse seen from a distant shore. These pulses are so regular and consistent that pulsars are often described as cosmic clocks, some of the most accurate timekeepers ever discovered in nature. The origin of a pulsar begins with the same violent process that creates a neutron star. After a massive star collapses in a supernova explosion, the remaining core becomes an extremely dense object composed mostly of neutrons. This object retains a significant amount of angular momentum from the original star, and as it collapses into a much smaller volume, its rotation speed increases dramatically. This is a direct consequence of conservation of angular momentum, the same principle that causes a spinning figure skater to rotate faster when pulling their arms inward. In some cases, this rotation becomes extremely rapid. A neutron star can spin multiple times per second, and in extreme cases, hundreds of times per second. When this rapid rotation is combined with a strong magnetic field, the conditions are set for the formation of a pulsar. The magnetic field of a neutron star is typically misaligned with its rotation axis, meaning that the magnetic poles are not aligned with the spin axis. This misalignment is crucial for the pulsar effect. The magnetic field of a neutron star is incredibly strong, often trillions of times stronger than Earth's magnetic field. This field channels charged particles along its lines, accelerating them to near light speed. At the magnetic poles, these particles emit beams of radiation across a wide range of the electromagnetic spectrum, including radio waves, X-rays, and sometimes gamma rays. These beams are highly focused and extend far into space. As the neutron star rotates, these beams sweep through space like the rotating beam of a lighthouse. If Earth lies in the path of one of these beams, we observe a pulse of radiation each time the beam points in our direction. This creates a periodic signal that repeats with extreme regularity. The interval between pulses corresponds directly to the rotation period of the neutron star. The discovery of pulsars in the late 20th century was initially so surprising that the first detected signals were even considered as possible evidence of extraterrestrial intelligence. The signals were extremely regular and precise, unlike most natural astrophysical sources. However, it was soon understood that these signals were produced by rapidly rotating neutron stars emitting beams of radiation. Pulsars are remarkable not only for their existence, but also for their precision. Some pulsars rotate with such stability that their periods rival or exceed the accuracy of the best atomic clocks on Earth. This stability is due to the enormous mass and compactness of neutron stars, which makes their rotation extremely stable over long periods of time. Even small changes in rotation can be measured with extraordinary precision. The regularity of pulsar signals allows scientists to use them as natural laboratories for studying a wide range of physical phenomena. By observing small variations in pulse timing, researchers can detect the presence of companion stars, measure gravitational effects, and even test the predictions of general relativity. Pulsars act as precise cosmic probes that allow us to study the universe in ways that would otherwise be impossible. One of the most important applications of pulsars is in the study of binary systems. Many pulsars exist in orbit with another star, often a white dwarf, neutron star, or even another pulsar. In these systems, the timing of pulsar signals can be affected by the gravitational influence of the companion object. By analyzing these variations, scientists can measure the masses of both objects and study the dynamics of their orbits. In some cases, pulsars are found in extremely tight binary systems where the two objects orbit each other very closely. In these systems, gravitational effects become very strong, and the emission of gravitational waves can cause the orbit to slowly decay over time. This process leads to measurable changes in pulsar timing, providing indirect evidence for the existence of gravitational waves long before their direct detection. Pulsars also provide a way to test the effects of strong gravity. Because they are so dense and compact, they exist in gravitational fields that are much stronger than anything found in the solar system. By studying how pulsar signals behave as they pass through curved space-time, scientists can test the predictions of general relativity in extreme conditions. Another important feature of pulsars is their emission across different wavelengths of light. While many pulsars are primarily detected through radio waves, others emit strongly in X-rays or gamma rays. These high-energy emissions are produced by particles accelerated to extreme speeds in the pulsar's magnetic field. The exact mechanisms behind these emissions are still an active area of research, as they involve complex interactions between magnetic fields, plasma, and relativistic particles. The environment around a pulsar is extremely energetic. The combination of rapid rotation, strong magnetic fields, and high-energy radiation creates a region of space filled with charged particles and intense electromagnetic activity. This region is often referred to as a pulsar wind nebula, where particles are accelerated outward and interact with surrounding material. In some cases, pulsars can create visible nebulae that glow across multiple wavelengths. These nebulae are powered by the energy released from the pulsar's rotation and magnetic field. As the pulsar slows down over time, it transfers energy into its surroundings, gradually losing rotational energy in the process. This energy loss is what causes pulsars to gradually slow their rotation over millions of years. Despite this gradual slowdown, pulsars remain highly stable over long periods. The rate at which they lose energy is extremely slow compared to human timescales. This makes them some of the most reliable natural clocks in the universe. Even small deviations in their timing can reveal important physical processes occurring within or around the neutron star. Pulsars also exhibit a phenomenon known as glitches. These are sudden changes in their rotation rate, where the pulsar briefly speeds up before returning to its previous behavior. Glitches are thought to be caused by interactions between the neutron star's crust and its superfluid interior. As stresses build up within the star, the crust can shift suddenly, transferring angular momentum from the interior to the surface and causing a temporary increase in rotation speed. These glitches provide valuable information about the internal structure of neutron stars. By studying how pulsars respond to these sudden changes, scientists can gain insight into the behavior of matter under extreme conditions, including the presence of superfluid components and the coupling between different layers of the star. The study of pulsars has also led to the development of pulsar timing arrays. These are networks of pulsars distributed across the sky that are monitored for extremely precise timing variations. By comparing the signals from multiple pulsars, scientists can detect very small distortions in space-time caused by passing gravitational waves. This method allows for the detection of low-frequency gravitational waves that are otherwise difficult to observe. Pulsars therefore play a crucial role in the emerging field of gravitational wave astronomy. They provide a way to study the universe not only through light, but also through the subtle ripples in space-time itself. This opens a new window into phenomena such as merging supermassive black holes and large-scale cosmic structures. The orientation of a pulsar's magnetic field also plays a key role in its behavior. The angle between the magnetic axis and the rotation axis determines the shape and intensity of the observed pulses. In some cases, both magnetic poles may be visible during a single rotation, producing complex pulse patterns. In other cases, only one beam is visible, resulting in simpler periodic signals. Over time, pulsars gradually lose energy and slow down. As their rotation decreases, their magnetic activity also weakens. Eventually, they may no longer produce detectable beams of radiation and become dormant neutron stars. This evolutionary path shows that pulsars are not permanent states, but phases in the long life of a neutron star. Despite their small size, pulsars have a significant impact on their surroundings. Their radiation and particle winds can shape nearby interstellar material, influence star formation in local regions, and contribute to the overall energy balance of the galaxy. In this way, they are not isolated objects, but active participants in galactic evolution. Pulsars also serve as natural experiments in extreme physics. They allow scientists to study how matter behaves under conditions of extreme density, magnetic field strength, and rotational speed. These conditions cannot be replicated on Earth, making pulsars unique tools for exploring fundamental physics. Each pulsar is a remnant of a massive star's death, but also a beacon of precision and stability in a chaotic universe. Their rhythmic signals travel across vast distances of space, carrying information about the most extreme environments known to science. In their regular pulses, we find both the echoes of stellar death and the rhythms of cosmic order. The extraordinary precision of pulsars is one of the most remarkable natural phenomena ever discovered in the universe. These rotating neutron stars emit beams of radiation that sweep across space with such regularity that they can be measured with astonishing accuracy. In many cases, the interval between pulses is more stable than the best atomic clocks built by humans. This makes pulsars not only fascinating astrophysical objects, but also powerful tools for studying time, gravity, and the structure of the universe itself. To understand why pulsars are so precise, it is necessary to return to their origin. A pulsar is formed when a massive star collapses and leaves behind a neutron star. During this collapse, the core of the star is compressed into an incredibly small volume while retaining most of its original angular momentum. As a result, the neutron star spins at extremely high speeds. This rapid rotation is remarkably stable because the star is extremely dense and has very little external influence that can disrupt its motion. In everyday objects, rotation tends to slow down quickly due to friction and external forces. However, a neutron star exists in near-vacuum conditions and has no significant friction to slow it down. Once formed, its rotation is governed almost entirely by conservation of angular momentum and internal physical processes. This is one of the key reasons why pulsars maintain such stable rotation over long periods of time. The emission of radiation from a pulsar is not continuous in all directions. Instead, it is focused into narrow beams aligned with the star's magnetic field. These beams are produced by charged particles that are accelerated along magnetic field lines near the magnetic poles. As these particles move at nearly the speed of light, they emit radiation across a broad range of wavelengths, including radio waves, visible light, X-rays, and gamma rays. Because the magnetic axis of a pulsar is usually tilted relative to its rotation axis, the radiation beams do not remain fixed in space. Instead, they sweep around as the star rotates. If Earth lies in the path of one of these beams, we observe a pulse of radiation each time the beam crosses our line of sight. This produces a highly regular pattern of signals that repeat with each rotation of the neutron star. The timing of these pulses is incredibly precise. Some pulsars can maintain rotational stability to within a fraction of a second over millions of years. This level of precision is comparable to the most advanced atomic clocks, which rely on quantum transitions in atoms to measure time. However, unlike artificial clocks, pulsars are natural objects that achieve this precision through their extreme physical properties. One of the key reasons for this stability is the enormous moment of inertia of neutron stars. Even though they are small in size, they contain more mass than the Sunday. This means that a large amount of energy is required to change their rotation speed. As a result, their spin is highly resistant to external disturbances. Small changes in energy or angular momentum have only minor effects on their rotation rate. Despite their stability, pulsars are not perfectly constant. Over very long timescales, they gradually lose energy through the emission of radiation and particle winds. This process is known as spin-down. As the pulsar emits electromagnetic radiation, it slowly transfers rotational energy into space, causing its rotation to slow down very gradually. However, this slowdown is extremely small and can often only be detected through precise long-term measurements. The ability to measure pulsar timing with extreme accuracy has led to the development of pulsar timing arrays. These are networks of carefully monitored pulsars spread across the sky. By measuring the arrival times of pulses from multiple pulsars, scientists can detect extremely small variations in space-time caused by gravitational waves. This method effectively turns pulsars into a galaxy-sized detector for studying the fabric of space-time. Pulsar timing arrays rely on the fact that gravitational waves passing through space can slightly stretch and compress space-time. This causes tiny changes in the arrival times of pulsar signals. By comparing data from many pulsars, scientists can identify correlated timing variations that indicate the presence of low-frequency gravitational waves. This technique complements ground-based detectors and opens a new window into the study of the universe. The precision of pulsars also allows them to be used as cosmic laboratories for testing fundamental physics. Because their signals are so regular, even the smallest deviations can be detected and analyzed. This makes pulsars ideal for studying effects such as gravitational time dilation, orbital motion in binary systems, and the propagation of light through curved spacetime. In binary systems, where a pulsar orbits another star or compact object, the timing of pulses can reveal detailed information about the system's dynamics. As the pulsar moves in its orbit, the distance between it and Earth changes slightly, causing variations in the arrival times of its signals. These variations can be used to determine the masses of both objects and to study the effects of gravity in strong field conditions. Some of the most precise tests of general relativity have been conducted using pulsar binary systems. In these systems, the effects of gravitational wave emission can be observed as a gradual decay in the orbital period. This decay matches the predictions of general relativity with remarkable accuracy, providing strong evidence for the existence of gravitational waves long before their direct detection. Pulsars also exhibit a phenomenon known as timing noise. This refers to small, irregular variations in their rotation that are not fully understood. Timing noise may be caused by changes in the star's internal structure, interactions between its crust and superfluid interior, or variations in its magnetic field. Studying these irregularities provides valuable insight into the internal physics of neutron stars. Another important aspect of pulsar timing is the study of glitches. Glitches are sudden increases in a pulsar's rotation speed, followed by a gradual return to its previous behavior. These events are thought to be caused by interactions between the rigid crust of the neutron star and its superfluid interior. As stress builds up within the star, angular momentum is transferred between different layers, resulting in a sudden change in rotation rate. Glitches provide important information about the internal structure of neutron stars. By analyzing the timing of these events, scientists can learn about the behavior of superfluid matter and the coupling between different regions of the star. This helps improve theoretical models of neutron star interiors and contributes to our understanding of matter under extreme conditions. The precision of pulsar timing is also affected by the interstellar medium. As pulsar signals travel through space, they pass through clouds of gas and charged particles. These materials can cause dispersion and scattering of the signals, leading to slight delays in their arrival times. By studying these effects, scientists can also learn about the structure and composition of the interstellar medium. Pulsars are therefore not only tools for studying neutron stars themselves, but also probes of the space between stars. Their signals carry information about both their origin and the medium through which they travel. This makes them valuable for studying multiple aspects of astrophysics simultaneously. In addition to their scientific importance, pulsars also represent one of the most stable natural phenomena known to science. Their regularity is so reliable that they have been considered as potential cosmic navigation beacons for spacecraft traveling through the galaxy. By measuring the timing of pulsar signals, it is theoretically possible to determine precise positions in space, similar to how GPS satellites are used on Earth. This concept, known as pulsar navigation, takes advantage of the predictable timing of pulsar emissions. A spacecraft equipped with a pulsar timing system could determine its location in space by comparing observed pulse arrival times with known pulsar timing models. This would allow for autonomous navigation in deep space without relying on Earth-based systems. The stability of pulsars also provides insight into the fundamental nature of time itself. Because their signals are so regular, they serve as natural references for measuring the passage of time across vast distances. This allows scientists to test whether physical laws remain consistent throughout the universe. In some cases, pulsar timing has revealed unexpected phenomena. For example, extremely precise measurements have shown that certain pulsars exhibit tiny irregularities that may be caused by interactions with orbiting planets or other objects. These discoveries demonstrate that even the most stable systems can contain hidden complexities. The precision of pulsars ultimately arises from the extreme conditions under which they exist. Their immense density, rapid rotation, and strong gravitational fields combine to create objects that are both highly stable and highly sensitive to subtle physical effects. This combination makes them ideal natural clocks and powerful tools for scientific exploration. Each pulse from a pulsar is a signal traveling across vast distances of space, carrying with it information about the most extreme environments in the universe. In their rhythmic precision, pulsars reveal the underlying order hidden within the most violent and energetic processes in nature. Among the most extreme objects in the universe, magnetars stand out as something even more intense than ordinary neutron stars and pulsars. They are neutron stars pushed to their absolute limits, where magnetic fields reach strengths so enormous that they reshape the behavior of matter, light, and even the structure of empty space around them. If pulsars are precise cosmic clocks, magnetars are chaotic engines of magnetic energy, capable of unleashing bursts of radiation that can briefly outshine entire galaxies in specific wavelengths. A magnetar begins its life in the same way as any other neutron star, born from the collapse of a massive star in a supernova explosion. In the core of the collapsing star, matter is crushed into neutron degenerate form, creating an object only about 20 kilometers across, but containing more mass than the Sunday. At this stage, the newborn neutron star is extremely hot, rapidly rotating, and highly energetic. It also possesses a magnetic field, which is a natural consequence of the motion of charged particles during and after collapse. However, what distinguishes a magnetar from a typical neutron star is the extraordinary amplification of its magnetic field. While ordinary neutron stars already have extremely strong magnetic fields, magnetars take this to another level entirely. Their magnetic fields can reach strengths on the order of 10 to the power of 15 Gauss, or even higher, making them trillions of times stronger than Earth's magnetic field. To put this into perspective, A magnetar's magnetic field is so powerful that it can distort atomic structures and affect the behavior of matter at a fundamental level. The exact mechanism behind the formation of such extreme magnetic fields is still an active area of research, but it is believed to involve a combination of rapid rotation and turbulent convection in the early stages of the neutron star's life. In the moments after the supernova collapse, the neutron star is highly unstable and dynamic. If it rotates fast enough, a dynamo effect can occur, amplifying magnetic fields to extraordinary levels. This process is similar in principle to how magnetic fields are generated in planets and stars, but under the extreme conditions of a neutron star, the amplification becomes far more powerful. Once established, the magnetic field of a magnetar dominates everything around it. It controls the motion of charged particles, shapes the star's emission of radiation, and even affects the structure of its crust. The magnetic field is so strong that it can distort the electron clouds of atoms, effectively changing the way matter behaves at microscopic scales. In such extreme conditions, the distinction between normal atomic physics and plasma physics begins to blur. The surface of a magnetar is not a calm or stable place. It is a highly stressed environment where the magnetic field exerts enormous pressure on the crust of the neutron star. Over time, this stress builds up as the magnetic field evolves and twists beneath the surface. The rigid crust is forced to adapt to these changing magnetic conditions, but it cannot do so indefinitely. Eventually, the stress becomes too great, and the crust cracks or shifts suddenly in what is known as a starquake. Starquakes on magnetars are far more energetic than those on ordinary neutron stars. When the crust fractures, it releases a tremendous amount of energy stored in the magnetic field. This energy is released in the form of high-energy radiation, including X-rays and gamma rays. These bursts can be incredibly powerful, sometimes releasing more energy in a fraction of a second than the sun emits in thousands of years. One of the most dramatic phenomena associated with magnetars is the giant flare. A giant flare is an extremely powerful outburst of gamma rays and X-rays that can briefly affect the entire galaxy in terms of high-energy radiation output. During such an event, the magnetar releases a sudden burst of energy as its magnetic field undergoes a large-scale reconfiguration. These flares are rare, but when they occur, they are among the most violent events known in the universe. The energy released during a giant flare is so intense that it can have measurable effects on nearby space environments. If a magnetar were located relatively close to Earth, such a flare could potentially affect the ionosphere and disrupt satellite communications. Fortunately, known magnetars are located at safe distances, typically thousands or tens of thousands of light-years away. The magnetic field of a magnetar also affects the vacuum of space itself. At such extreme field strengths, quantum electrodynamic effects become important. One of these effects is vacuum birefringence, where empty space behaves like a medium that can alter the polarization of light passing through it. This means that even the vacuum is no longer truly empty in the classical sense when exposed to a magnetar's magnetic field. Matter near a magnetar behaves in highly unusual ways. Atoms cannot exist in their normal form because the magnetic field is strong enough to distort electron orbits. Electrons are forced into tightly confined states along magnetic field lines, creating elongated atomic structures. This changes the chemical and physical properties of matter in ways that are completely different from anything observed under normal conditions. The surface of a magnetar is thought to consist of a solid crust of ultra-dense matter, similar to that of other neutron stars, but this crust is constantly under magnetic stress. The magnetic field can twist and shear the surface, creating fractures and rearranging the structure of the crust. These processes are slow on human timescales, but can lead to sudden and violent releases of energy. Above the surface, the magnetar is surrounded by a magnetosphere filled with charged particles trapped by the magnetic field. These particles are constantly accelerated along magnetic field lines, producing high-energy radiation. The magnetosphere of a magnetar is highly dynamic and can change rapidly during periods of activity. It is in this region that much of the observed radiation from magnetars is generated. Magnetars also emit persistent X-ray radiation, even when they are not undergoing flares. This steady emission is thought to be powered by the gradual decay of their magnetic fields. Unlike ordinary neutron stars, which lose energy primarily through rotational slowdown, magnetars lose energy through the decay and rearrangement of their magnetic fields. This makes their evolution fundamentally different from that of typical pulsars. Over time, the magnetic field of a magnetar gradually weakens. As it decays, the energy stored in the field is released into space in the form of radiation. This process can take thousands to millions of years, depending on the initial strength of the field. As the magnetic field weakens, the magnetar becomes less active and may eventually evolve into a more typical neutron star. The extreme conditions near a magnetar also influence the surrounding interstellar environment. High-energy radiation emitted during flares can ionize nearby gas clouds and affect the chemistry of interstellar matter. In this way, magnetars can play a role in shaping their local cosmic environment, despite their relatively small size. Magnetars are also of great interest because they provide a natural laboratory for studying physics under conditions that cannot be replicated on Earth. The combination of extreme gravity, ultra-strong magnetic fields, and dense nuclear matter creates an environment where multiple branches of physics intersect. This includes quantum mechanics, electromagnetism, and general relativity. One of the key questions in magnetar research is how their magnetic fields evolve over time. The decay of these fields is not fully understood, and different models suggest different mechanisms, including crustal motion, magnetic reconnection, and internal field rearrangement. Understanding this process is essential for explaining the observed behavior of magnetars and their emission of radiation. Magnetars are also linked to some of the most mysterious events in astrophysics, known as fast radio bursts. These are extremely brief but intense bursts of radio waves coming from distant galaxies. One leading theory suggests that at least some fast radio bursts may be caused by magnetar flares. If this is true, then magnetars could be responsible for some of the most energetic and short-lived signals in the universe. The study of magnetars continues to evolve, as new observations and instruments become available. Space-based telescopes capable of detecting X-rays and gamma rays have provided valuable data on their behavior, revealing the complexity of their magnetic environments and the diversity of their activity. In many ways, magnetars represent the extreme limit of what a neutron star can become. They are objects where magnetic energy dominates all other forms of energy, where matter is distorted by invisible forces, and where the boundary between classical physics and quantum physics becomes blurred. Each magnetar is a reminder that the universe is capable of producing conditions far beyond human experience. They are not just remnants of dead stars, but active, evolving systems powered by some of the strongest forces in nature. In their violent bursts and silent magnetic evolution, magnetars reveal a universe shaped not only by gravity, but also by the hidden power of magnetic fields at cosmic scales. In the universe, few systems are as dynamic and violent as binary systems involving neutron stars. When a neutron star exists with a companion star, the interaction between the two objects can create some of the most energetic and complex astrophysical phenomena known. These systems are often described as stellar cannibals because the neutron star can pull matter from its companion, feeding on it through the immense force of gravity. This process transforms both objects and produces intense radiation that can outshine entire star systems. A binary system begins when two stars are born close enough together that they remain gravitationally bound throughout their lives. In many cases, both stars may begin as ordinary main sequence stars, but they do not evolve at the same rate. The more massive star exhausts its nuclear fuel more quickly and eventually undergoes a supernova explosion, leaving behind a neutron star. The companion star, however, may still be in a relatively stable phase of its life. Once the neutron star is formed, the system becomes fundamentally different. The neutron star, with its extreme density and gravity, begins to influence its companion in profound ways. If the two stars are close enough, the neutron star's gravity can begin to pull material away from the outer layers of the companion star. This process is known as mass transfer, and it is one of the key mechanisms that drives binary evolution involving neutron stars. The material that is pulled from the companion does not fall directly onto the neutron star in a straight line. Instead, it forms an accretion disk around the neutron star. This disk is a rotating structure of gas and plasma that gradually spirals inward due to friction and gravitational forces. As the material moves closer to the neutron star, it becomes increasingly hot and energetic. The accretion disk is one of the most important sources of radiation in the universe. As matter spirals inward, it releases gravitational potential energy, which is converted into heat and electromagnetic radiation. This process can generate enormous amounts of energy, particularly in the form of X-rays. In fact, many neutron star binary systems are among the brightest X-ray sources in the sky. The inner regions of the accretion disk are extremely hot, reaching temperatures of millions of degrees. At these temperatures, atoms are fully ionized, and the gas exists as a plasma of charged particles. The motion of this plasma is influenced by both gravity and magnetic fields, creating complex and turbulent flow patterns. The interaction between the disk and the neutron star's magnetic field plays a crucial role in shaping the behavior of the system. In some cases, the neutron star's magnetic field is strong enough to disrupt the inner part of the accretion disk. When this happens, the material is funneled along magnetic field lines directly onto the magnetic poles of the neutron star. This creates hot spots on the surface that emit intense radiation. As the neutron star rotates, these hot spots can produce periodic pulses of X-ray or radio emission. This process can lead to the formation of accreting pulsars, where the neutron star emits regular pulses due to the combination of rotation and accretion. These systems are highly variable, with changes in accretion rate leading to changes in brightness and emission patterns. The interaction between accretion and magnetic fields creates a dynamic and constantly evolving environment. Binary systems involving neutron stars can take many different forms depending on the nature of the companion object. If the companion is a normal star, mass transfer can occur over long periods of time as the star expands during its evolution. If the companion is a white dwarf or another compact object, the interactions can be even more extreme. In some systems, both objects are neutron stars. These double neutron star systems are particularly important for the study of gravitational physics. As the two neutron stars orbit each other, they emit gravitational waves which carry energy away from the system. This causes the orbit to gradually shrink over time, eventually leading to a merger. The emission of gravitational waves from binary neutron star systems was one of the first indirect confirmations of Einstein's general theory of relativity. The observed decay of orbital periods in these systems matched the predictions of gravitational wave emission with remarkable accuracy. This provided strong evidence that space-time itself can carry energy away from massive systems. When two neutron stars eventually merge, the result is one of the most violent events in the universe. The collision releases enormous amounts of energy in the form of gravitational waves, gamma-ray bursts, and electromagnetic radiation. These events are known as kilonovae because of their brightness, which is roughly 1,000 times greater than a typical nova. During a neutron star merger, matter is compressed and heated to extreme temperatures. The collision can eject large amounts of material into space at high speeds. This ejected material is rich in neutrons and becomes the site of rapid neutron capture processes known as the R process. This process is responsible for the creation of many of the heavy elements in the universe, including gold, platinum, and uranium. The production of heavy elements in neutron star mergers is one of the most important discoveries in modern astrophysics. It provides a direct link between the most extreme astrophysical events and the chemical composition of planets and life itself. The gold in jewelry and the heavy elements in Earth's crust may have originated from ancient neutron star collisions. The energy released during these mergers is so great that it can be detected across vast distances of space. In 2017, the first observed neutron star merger was detected both through gravitational waves and electromagnetic signals. This event marked a major milestone in multi-messenger astronomy, where different types of signals are combined to study cosmic phenomena. Binary neutron star systems also play a role in the formation of millisecond pulsars. These are neutron stars that rotate extremely rapidly, often hundreds of times per second. It is believed that these fast-rotating pulsars are formed when a neutron star accretes matter from a companion star. As material falls onto the neutron star, it transfers angular momentum, causing the star to spin faster and faster over time. This process effectively recycles old neutron stars, giving them a new lease on life as rapidly rotating pulsars. Millisecond pulsars are some of the most stable and precise rotators in the universe, and they are often found in binary systems where accretion has played a major role in their evolution. The interaction between neutron stars and their companions can also lead to dramatic variability in brightness. Some systems undergo periods of intense activity followed by quieter phases, depending on the rate of mass transfer. These changes can occur over timescales ranging from days to years. In extreme cases, the accretion process can become unstable, leading to sudden bursts of radiation. These bursts are caused by rapid infall of material onto the neutron star surface, releasing large amounts of energy in a short period of time. Such events are observed as X-ray bursts and provide insight into the behavior of matter under extreme pressure and temperature. The study of binary neutron star systems is essential for understanding the life cycles of stars and the dynamics of compact objects. These systems represent some of the most complex interactions in astrophysics, involving gravity, magnetic fields, nuclear physics, and relativistic effects all at once. They also serve as important sources of gravitational waves. As detectors such as LIGO and Virgo observe these waves, scientists can study the properties of neutron stars in unprecedented detail. The waveforms produced during inspiral and merger events carry information about the masses, radii, and internal structure of the stars involved. Binary systems involving neutron stars also influence the evolution of galaxies. The energy released during accretion and mergers contributes to the heating and enrichment of the interstellar medium. The heavy elements produced in these systems are dispersed throughout space, becoming part of future generations of stars and planets. In this way, neutron star binaries are not isolated phenomena, but active participants in the cosmic cycle of matter and energy. They connect the death of massive stars to the formation of new structures in the universe, linking different stages of cosmic evolution. Each binary system is a unique laboratory where extreme physics unfolds. The interactions between neutron stars and their companions reveal the power of gravity to shape matter on both small and large scales. They show how simple orbital motion can lead to some of the most energetic events in the cosmos. In the end, binary systems involving neutron stars are not just about destruction or consumption, they are about transformation. Through the transfer of mass, the emission of radiation, and the generation of gravitational waves, these systems continuously reshape themselves and their surroundings. They stand as some of the most dynamic and influential structures in the universe, where gravity and matter engage in a constant and dramatic exchange. When two neutron stars spiral toward each other and collide, the universe reaches one of its most extreme states of violence and transformation. These events are not gradual or quiet. They are sudden, catastrophic mergers where matter, gravity, and space-time itself are pushed to their limits. In a matter of seconds, two of the densest objects in existence can combine into a single remnant, releasing more energy than most stars produce over their entire lifetimes. These collisions are not only visually and physically dramatic, they are also one of the most important processes for shaping the chemical evolution of the universe. The story of a neutron star collision begins long before the final impact. In a binary system where two neutron stars orbit each other, the system slowly loses energy over time. This loss is not due to friction in the traditional sense, because space is nearly a perfect vacuum. Instead, the energy is carried away by gravitational waves, ripples in space-time, predicted by Einstein's theory of general relativity. These waves propagate outward at the speed of light, gradually extracting energy from the system and causing the two neutron stars to spiral closer together. At first, this process is extremely slow. The stars may orbit each other for millions or even billions of years, slowly tightening their orbit as gravitational waves carry away energy. But as they get closer, the rate of energy loss increases. The orbit shrinks faster and faster, and the stars begin to move at significant fractions of the speed of light. In the final moments before collision, the system becomes incredibly dynamic, with extreme gravitational and relativistic effects dominating the motion of both stars. As the neutron stars approach each other, tidal forces become increasingly important. Each star exerts enormous gravitational pull on the other, distorting their shapes. Although neutron stars are extremely rigid due to their dense matter, they are not completely immune to tidal deformation. In the final orbits, the stars begin to stretch slightly along the line, connecting them, creating subtle but important changes in their structure. These deformations also influence the gravitational wave signal emitted by the system. The final seconds before merger are among the most energetic in the universe. The neutron stars orbit each other hundreds of times per second, moving at velocities approaching a significant fraction of the speed of light. The gravitational waves emitted during this phase carry detailed information about the masses and internal structure of the stars. These signals can be detected by instruments such as gravitational wave observatories, allowing scientists to reconstruct the final moments of the inspiral. When the two neutron stars finally collide, the impact is not like a simple crash between solid objects. Instead, it is a complex interaction of ultra-dense matter governed by gravity and nuclear forces. The surfaces of the stars come into contact at relativistic speeds, creating shock waves that compress and heat the matter to extreme temperatures. In an instant, the structure of both stars is disrupted, and matter is ejected into space at tremendous velocities. The collision releases an enormous burst of gravitational waves. This signal carries away a significant portion of the system's energy in the form of space-time distortions. At the same time, electromagnetic radiation is emitted across the spectrum, from gamma rays to visible light. The combination of gravitational and electromagnetic signals makes neutron star mergers some of the most important sources for multi-messenger astronomy. One of the most dramatic outcomes of a neutron star collision is the formation of a kilonova. A kilonova is an extremely bright astronomical event powered by the radioactive decay of heavy elements created during the merger. As neutron-rich material is ejected from the collision, it undergoes rapid neutron capture, known as the R process. This process builds up heavy atomic nuclei in a very short period of time, producing elements such as gold, platinum, and many others that are heavier than iron. The R process occurs because the ejected matter is extremely rich in neutrons. In this environment, atomic nuclei rapidly capture neutrons before they can decay. As these nuclei become more and more neutron-rich, they eventually undergo beta decay, transforming neutrons into protons and moving towards stability. This sequence of reactions builds up some of the heaviest elements in the periodic table. The kilonova glow is powered by the radioactive decay of these newly formed elements. As unstable nuclei decay, they release energy in the form of light and heat. This energy heats the ejected material, causing it to emit radiation that can be observed for days or weeks after the initial collision. Although kilonovae are not as bright as supernovae in visible light, they are extremely important for understanding the origin of heavy elements in the universe. Before the discovery of neutron star mergers as sites of heavy element production, the origin of many elements beyond iron was not fully understood. While supernovae were long thought to be responsible for element formation, they could not fully account for the abundance of certain heavy elements. The observation of kilonovae provided strong evidence that neutron star collisions are a major source of these elements. The first confirmed observation of a neutron star merger occurred in 2017, when both gravitational waves and electromagnetic signals were detected from the same event. This marked a turning point in astrophysics, confirming that gravitational waves and light could be observed from a single cosmic event. The gravitational wave signal showed the in-spiral and merger of two neutron stars, while the electromagnetic counterpart revealed the kilonova and the production of heavy elements. The collision itself results in the formation of a remnant object. Depending on the total mass of the system, this remnant may be a more massive neutron star, or it may collapse into a black hole. If the combined mass exceeds a critical threshold, known as the maximum mass limit for neutron star stability, gravitational collapse becomes inevitable, and a black hole is formed almost immediately after the merger. If a black hole is formed, some of the surrounding material may remain in orbit, forming an accretion disk. This disk can continue to emit radiation as it gradually falls into the black hole. In some cases, this process may produce short gamma-ray bursts, which are extremely brief but intense flashes of gamma radiation observed from distant galaxies. These bursts are thought to be associated with the formation of black holes following neutron star mergers. The gravitational waves produced during the merger carry detailed information about the internal structure of neutron stars. As the stars spiral inward, their tidal interactions affect the waveform of the emitted gravitational radiation. By analyzing these signals, scientists can place constraints on the equation of state of neutron star matter, which describes how matter behaves at extreme densities. The study of neutron star collisions therefore provides insight into both astrophysics and fundamental physics. It connects the behavior of matter under extreme conditions with the dynamics of space-time itself. It also reveals how elements are created and distributed throughout the universe. The energy released in a neutron star merger is so immense that it can briefly outshine entire galaxies in certain wavelengths. However, this energy is not emitted evenly. It is distributed across gravitational waves, gamma rays, X-rays, visible light, and radio waves, each carrying different information about the event. This makes neutron star mergers some of the most complex and information-rich phenomena in the universe. After the initial collision, the remnant environment continues to evolve. The ejected material expands into space, interacting with surrounding interstellar gas. Over time, this material mixes with the galaxy, enriching it with newly formed heavy elements. These elements eventually become part of new stars, planets, and even life itself. The importance of neutron star collisions extends far beyond the immediate event. They are part of the cosmic cycle of matter, where the death of one system leads to the creation of new chemical complexity elsewhere. Without these collisions, many of the heavy elements found on Earth would not exist. The detection of gravitational waves from neutron star mergers has opened a new era in astronomy. It allows scientists to observe the universe not only through light, but also through the vibrations of space-time itself. This new form of observation provides a completely different perspective on cosmic events. Each collision between neutron stars is a rare and extraordinary event. It represents the final stage in the life of a binary system that may have existed for billions of years. In the final moments, gravity takes over completely, drawing the stars together in a spiral of increasing speed and energy until they merge in a single, violent instant. In the aftermath, the universe is briefly illuminated by one of its most powerful explosions. Heavy elements are forged, space-time is shaken, and a new compact object is formed. Whether that object is a massive neutron star or a black hole, the system is forever changed. Neutron star collisions demonstrate that the universe is not static, but constantly evolving through cycles of creation and destruction. They show how gravity can bring together the densest objects in existence and transform them into new forms of matter and energy. In these collisions, we see both the destruction of old structures and the creation of the building blocks of future worlds. The life of a neutron star does not end in a single moment. Unlike a supernova, which is explosive and immediate, the evolution of a neutron star is slow, subtle, and stretched across timescales that can exceed the age of entire civilizations. These objects are born in violence, shaped by extreme physics, and then left to evolve in relative isolation, gradually changing as they lose energy, interact with their surroundings, and respond to the fundamental forces that govern their existence. The fate of neutron stars is deeply connected to some of the most important questions in astrophysics, including the limits of matter, the nature of gravity, and the ultimate structure of the universe. In the earliest phase of its life, a neutron star is extremely hot and highly active. It may rotate rapidly, emit intense radiation, and possess a magnetic field strong enough to shape its environment. But this is only the beginning. Over time, the neutron star begins to cool. The initial heat, generated during its violent formation and collapse, gradually escapes in the form of neutrinos and thermal radiation. Because neutron stars are incredibly dense, their cooling process is slow compared to ordinary stars, but it is steady and continuous. As the neutron star cools, its internal structure begins to settle. The outer layers, known as the crust, remain solid and extremely rigid. Beneath this crust, the matter may exist in exotic states such as superfluid neutrons and superconducting protons. These quantum states are not just theoretical possibilities, but essential features of neutron star interiors. They influence how the star rotates, how it responds to stress, and how it evolves over time. One of the most important long-term processes affecting neutron stars is the gradual loss of rotational energy. Many neutron stars are born spinning rapidly due to the conservation of angular momentum during collapse. However, this rotation is not permanent. Over time, the neutron star loses energy through electromagnetic radiation and particle winds. This process is known as spin-down. As the star emits radiation, it slowly transfers rotational energy into space, causing its rotation to decrease. This spin-down process is extremely gradual. In some cases, it can take millions or even billions of years for a neutron star to significantly slow its rotation. However, even small changes in rotation can have important consequences. The slowing of rotation affects the magnetic field structure, the emission of radiation, and the overall stability of the star. As neutron stars age, their magnetic fields also evolve. The magnetic field is one of the defining features of these objects, and it plays a crucial role in their behavior. In some neutron stars, the magnetic field remains relatively stable over long periods. In others, especially magnetars, the field can decay significantly over time. This decay is driven by processes such as magnetic reconnection, crustal movement, and internal dissipation of magnetic energy. The decay of magnetic fields leads to a reduction in the star's high-energy activity. Young neutron stars and magnetars can produce intense bursts of X-rays and gamma rays, but older neutron stars tend to become quieter. As the magnetic field weakens, the star emits less radiation and becomes more difficult to detect. In many cases, neutron stars eventually transition into a state where they are no longer observable as pulsars. This occurs when their rotation slows to the point where they no longer produce detectable beams of radiation. At this stage, the neutron star becomes a dormant object, still present in space, but no longer actively emitting strong signals. These objects are sometimes referred to as dead or extinct pulsars, although they continue to exist physically. Despite becoming less active, neutron stars do not disappear. They remain extremely dense and gravitationally significant objects. Their presence continues to influence nearby space, especially in binary systems or regions with strong gravitational interactions. Even a dormant neutron star retains its mass, magnetic remnants, and internal structure. Over extremely long timescales, neutron stars continue to cool. Eventually, they may reach a state where thermal radiation becomes negligible. In theory, they would become cold, dark, and invisible objects, often described as black neutron stars or cold stellar remnants. However, the universe is not yet old enough for any neutron star to have reached this final state. The timescales required are far longer than the current age of the universe. The ultimate fate of a neutron star depends heavily on its environment and interactions. If it exists in isolation, it may simply continue cooling and slowing down indefinitely. However, if it is part of a binary system, its evolution can take a very different path. In such systems, the neutron star may accrete matter from a companion star, leading to renewed activity and changes in its structure. Accretion can significantly alter the evolution of a neutron star. As matter falls onto the surface, it transfers both mass and angular momentum. This can cause the neutron star to spin up, sometimes transforming it into a millisecond pulsar. This recycling process effectively rejuvenates old neutron stars, giving them new rotational energy and renewed emission activity. However, accretion also has limits. If enough mass is added to the neutron star, it may reach a critical threshold where it can no longer support itself against gravitational collapse. This threshold is known as the Tolman-Oppenheimer-Volkoff limit. If the mass exceeds this limit, the neutron star will collapse into a black hole. This transition represents the ultimate fate for many neutron stars in binary systems. The formation of a black hole from a neutron star marks the end of one phase of stellar evolution and the beginning of another. In this process, matter is compressed beyond the neutron degeneracy limit, and gravity overwhelms all other forces. The result is a region of space-time from which nothing, not even light, can escape. However, not all neutron stars end in collapse. Many will remain stable for extremely long periods of time. In fact, some neutron stars may persist for timescales far exceeding the current age of the universe. These ancient objects serve as relics of earlier cosmic epochs, preserving information about the conditions under which they formed. Neutron stars also play an important role in the broader evolution of galaxies. Through processes such as supernova explosions, binary interactions, and neutron star mergers, they contribute to the distribution of heavy elements throughout space. Elements such as gold, platinum, and uranium are produced in these extreme environments and dispersed into the interstellar medium, where they become part of future generations of stars and planets. In this sense, neutron stars are not isolated endpoints, but active participants in the cosmic cycle of matter. They help recycle material from old stars into new systems, ensuring that the chemical complexity of the universe continues to grow over time. Another important aspect of neutron star evolution is their role as gravitational laboratories. Because they exist in such extreme conditions, they allow scientists to test theories of physics that cannot be studied elsewhere. Observations of neutron stars provide constraints on the behavior of matter at nuclear densities, the properties of superfluids and superconductors, and the nature of space-time under strong gravity. As observational technology improves, scientists are able to study neutron stars in greater detail. Radio telescopes, X-ray observatories, and gravitational wave detectors all contribute different pieces of information. Together, these observations help build a more complete picture of how neutron stars evolve over time. Gravitational wave astronomy in particular has opened a new window into neutron star evolution. By observing the signals produced during neutron star mergers, scientists can study the final stages of binary evolution and the conditions that lead to black hole formation. These observations also provide insight into the internal structure of neutron stars and the behavior of matter at extreme densities. Even in their final stages, neutron stars continue to influence their surroundings. If they remain in binary systems, their gravitational interactions can shape the orbits of nearby objects. If they are isolated, they still contribute to the gravitational landscape of the galaxy. In some theoretical scenarios, extremely old neutron stars may become so cold and dark that they are nearly impossible to detect. These objects would still exist, but they would emit almost no radiation and would be effectively invisible against the background of space. They would represent one of the final stages of stellar evolution, long after their original formation in supernova explosions. The study of neutron star evolution is not just about understanding individual objects, but about understanding the life cycle of matter in the universe. From the collapse of massive stars to the formation of exotic compact objects, neutron stars represent a key link in the chain of cosmic evolution. They are born in explosions, shaped by extreme forces, transformed by interactions, and eventually fade into quiet remnants or collapse into black holes. Throughout this process, they influence their surroundings, contribute to the chemical enrichment of the universe, and provide insights into the fundamental laws of physics. In the end, neutron stars remind us that the universe is constantly changing. Even the most extreme and stable objects are not permanent. They evolve, interact, and eventually transform into something new. Their existence reveals a universe governed by cycles of creation, transformation, and destruction, where even the densest objects in nature are part of a larger cosmic story.